All right, this is an example, completely an example of our project part one. Remember, there's going to be multiple parts to this for the rest of the semester. It's basically extending the distance ladder out into the universe. All right, so remember our first distance was using just an ordinary parallax. Now what we're doing is we're extending this out to using spectroscopic parallax. All right, so in my example here, what we're going to do is we're going to choose star E. That stands for example star. And just remember a couple of things here. So it's really important to remember that 1 parsec is equal to approximately 3.1 times 10 to the 16th meters. Okay, so we need that. For my example star, the temperature of my example star is measured to be, remember you can measure that by finding the peak wavelength, or you can also measure it by looking at the different colors using like a V and a B filter, or a B and a V, B minus V filter. So you filter it anyhow. You filter it in the blue, and then you filter it in the visible, and you subtract the two, and that is actually that's actually how astronomers generally find the temperature. Right? It's very time consuming to look at the entire spectrum and find the actual peak. Anyhow, however it's done. We found that this example star has a temperature of 4,000 Kelvin. And its apparent brightness, now that's something that you can measure in the telescope, is measured at 4.7 times 10 to the minus 11th in watts per square meter. Okay, so now the job, and this is exactly like the problem that is given to you with the star Sirius. So now what we want to do is we want to find the absolute luminosity of this star, or my example star here, from the HR diagram. All right, so we're going to do that. All right, so here's the HR diagram. This is the exact one that was given to you, right? Look there's the problem, for example. So, but remember, we're using my example problem because you guys will use the information from, for Sirius, and there it all is. But you're going to do the same steps. All right, so the spectral class, since this is this one turns out to be exactly 4,000 Kelvin. I chose that for a reason. So you can see that that's an M class star. Anyhow, the idea is, I guess I should have said that it's a class 5 star as well, so that puts it, that's on the main sequence. That's actually really important. I think we're going to assume that it's on the main sequence, okay? Just like the star Sirius is on the main sequence. Anyhow, it's on the main sequence, and so you look here. So this is where it's a little bit tricky, okay? Remember, this is an approximation. I want everybody to understand that it's an approximation. All right. So if I find this 400 Kelvin, all right. So there it is across the top, 400 Kelvin, and then I drop a straight line. Okay. So I got to go straight down until I reach the main sequence. All right. So there's the main sequence. Right. That's this line right here. I shouldn't have moved that. So there's 4,000 to drop it straight down. It was kind of straight. All right, and then now I'm on the main sequence, and so then I look to the left, and that's the luminosity in terms of the luminosity of the sun. And so what's the absolute luminosity of the star? So I just go straight over from the HR diagram. From the main sequence on the HR diagram. So I go just straight over, and so I'm kind of trying to go straight over. So from where I was to straight over. Notice I picked this specifically so that we'd have if you were in between here, you'd have to estimate where it is, right? So this would be, something up here would be one times the luminosity of the sun. Something about in the midpoint between 1 and 1/100th would be 1/10. All right, so somewhere around. But this one happens to be 10 to the -2, which is 1/100th. So that's the absolute luminosity. The absolute luminosity, because of the temperature of the because of the spectral class, which is why that's its temperature, its luminosity, if as long as it's on the main sequence, is 10 to the -2. All right, so now we're ready to do the rest of the problem. Right, and so we just did this. So from the luminosity of our example star is equal to 10 to the -2 times the luminosity of our sun. All right, and you might remember that value, the luminosity of our sun, is 4 times 10 to the 26th watts per square meter. All right, so let's continue this problem. Let me get a new screen. So the important things that was from the last slide that we had was that the flux of our example star E was, arriving at our telescope, was 4.7 times 10 to the -11th watts per square meter, and you can that is a way of saying that's the absolute, the apparent magnitude, right? That's how bright the star is in our telescope. All right, so remember, from the HR diagram, we learned that the luminosity, the absolute luminosity of star E, is 1/100th times the luminosity of the sun. So that's going to be 10 to the -2 times the luminosity of the sun, which is 4 times 10 to the 26th watts per square meter. All right, remember, we always get these values, some number times the luminosity of our sun. All right, so the important question is, how do you get the distance, right? So we use the inverse square law, right? This is the inverse square law. The flux, that is the energy that arrives at your telescope, is equal to the luminosity, how powerful that particular star is, divided by 4 pi times the distance squared. Okay, so we have to rearrange this and solve for the distance, right? And so that's pretty simple. So this so the d and the f change places, and then we got to take the square root, right? So this d is going to equal, so it's the square root of all this stuff. So it's the square root of the luminosity in of course solar units, divided by 4 pi, and divided by the flux of our, so both of these are for our star, right? The luminosity of our star, of the example star, and the flux of our example star. All right, let me put the numbers in. All right, so all I've done is I put the numbers in. So it's the luminosity is 10 to the -2 times 4 times 10 to the 26, and then all that is divided by 4 pi times the apparent magnitude, which is 4.7 times 10 to the -11th. Of course, both of these are in watts per square meter, so the watts per square meter cancels, and that'll give us an answer in meters. Okay, so let's see what we have. So when I did this, I get 8.8. So this comes out to be 8.23 times 10 to the 16th. 10 to the 16th meters. All right, and of course we would like to know what that is in parsecs. All right, so this is what you do remember the L came from the HR diagram, and because we knew the temperature, we could estimate what L was, and the flux was given to us, and so we just kind of rearrange this equation and solve for the distance, and the answer comes out in meters. And now let's convert meters to parsecs. Okay, so it's going to be, 1 parsec, of course, is 3.1 times 10 to the 16th meters. And so I'll do that. All right, so I just made a new page here. So this is what the distance turned out to be when we solved it, but we would like that to be not in meters. We'd like it to be in parsecs. I'm going to even change it to light years as well. So it turns out that 1 parsec, all right, you can just look this up, is 3.1, approximately 3.1 times 10 to the 16th meters. All right, so of course the meters cancel, and so we divide those two numbers, and I get 2.65. So 2.65 parsecs. So that's how far away this star is. You could also do it in the following way. So if we know that it's 2.65 parsecs, we could even change it to light years, which is always not a bad option. So of course we know that in 1 parsec there are 3.26 light years, and so of course the parsecs cancel, and so that's equal to 8.65. So 8.65 light years. All right, so either of these answers are perfectly acceptable. I can't remember if the sheet, the worksheet asks you to. I mean, of course you're going to do it. You're going to calculate this in meters first, and then you're going to convert it to parsecs. I don't think you have to change it to light years, but if you want to, you can certainly do that. That's an option. So then, of course, answer those questions. There's several questions to answer, but this is the main steps that you're going to take. Remember, getting the luminosity from what the surface temperature of the star is. There's a little bit of uncertainty in that, right? Because you're looking at a logarithmic scale, and you're making your best educated guess at what that luminosity is. All right. So, but you go through the exact same steps that I did, but you're going to use the star Sirius, and the brightest star in the night sky, and so that's project 1. Okay, so that's stellar parallax, and then of course you could compare that. Here, let's since I'm talking about it, you could compare that to actual parallax. Like if you know the parallax to a star, I didn't make up this particular one, but if you know the parallax to the star, of course, in arc seconds, you could figure out the distance in parsecs. So let's say you were given what the parallax is, or you could just look up the parallax of the star Sirius, and then you just it's in arc seconds, and then you'd solve that. And so this method, of course, is directly measuring the distance to a star using parallax, right? Spectral parallax is using the HR diagram, to estimate what the luminosity is, right? So you figure out what the spectral class is, and then you figure out what the luminosity is. All right, so that does it for project 1. Remember, you have to turn that in on Blackboard. All right.